Today we shall see the Diophantine equation Ax plus By equal to C. You have seen the congruence equation Ax congruent to B mod M, and this has solutions if and only if the GCD of A and M divides B. Here we shall see this equation Ax plus By equal to C, and we want solutions for this in integers. Here we have a similar condition for existence of solution. So ABC are integers. We can assume that at least one of A and B is not equal to 0. Because if both A and B are 0, then the equation becomes 0 times x plus 0 times y equal to C, and in this case if C is not equal to 0, then there is no solution, no integer solution. If C is 0, you can say that every integer is a solution to the equation. So that is a trivial case, that if A equal to 0, B equal to 0, then for C not equal to 0, no integer solution. And for C equal to 0, every integer x and every integer y gives a solution. So that's a trivial case, A equal to 0, B equal to 0. So let us assume that at least one of A and B is not equal to 0. So ABC integers, at least one of AB is non-zero. That's the assumption. Then what are all the solutions? So the solutions will exist only if GCD of A and B divides C. So if G equal to GCD of A and B and G does not divide C, then the equation Ax plus By equal to C has no solution in integers. Because G divides left hand side, so G has to divide right hand side. Now suppose this GCD G divides the right hand side C. So suppose G divides the right hand side C. In this case, we want to show that there are solutions in integers, and there are infinitely many solutions, and we can give them by some formula in terms of one solution of the equation. Suppose G divides C, the GCD G is an integer combination of A and B. So write A x naught plus B y naught equal to the GCD, where x naught y naught are integers. Now if C is G times C1, if C is G times C1, where C1 belongs to Z, then multiply this by C1. So A x naught C1 plus B y naught C1 equal to G C1, that's equal to C. That gives the solution. Therefore, x1 equal to x naught C1, y1 equal to y naught C1 is a solution to equation 1. Because here this is A times x1 plus B times y1 is equal to C. So you get a solution. Now suppose there is any other solution. Now A x1 plus B y1 equal to C. If x y satisfies Ax plus By equal to C, then you take the difference A times x minus x1 plus B times y minus y1 equal to 0. Now divide by the GCD. GCD of A and B. Therefore, A by G into x minus x1 plus B by G into y minus y1 is equal to 0. Now, A by G and B by G, they are coprime. GCD of A by G and B by G is 1. So, B by G, that because it is coprime to this, and B by G divides this term, because B by G divides the second term, so B by G will divide this first term, but B by G is coprime to A by G. Therefore, B by G must divide x minus x1. So, x minus x1 is a multiple of B by G. It is k times B by G for some integer k. B by G divides A by G times x minus x1, and it is coprime to A by G. Therefore, B by G divides x minus x1. Therefore, there is an integer k such that x minus x1 is equal to k times b by g, that is x equal to x1 plus k b by g. Now, if x minus x1 is k times b by g, from this equation, let us call this as equation number 2. So, substitute x minus x1 is equal to k times b by g. So, b by g gets cancelled and we get y minus y1 equal to minus a by g, y minus y1 equal to minus a by g times this k. From 2, y minus y1 equal to minus k into a by g, and therefore y equal to y1 minus k into a by g. So, we get x equal to x1 plus k into b by g, y equal to y1 minus k into a by g. Also, for any k, any integer k, these values will satisfy the equation a into x1 plus k times b by g plus b into y1 minus k into a by g. If you calculate this, a k b by g minus b k a by g, that gets cancelled, and a x1 plus b y1, and that's equal to c, because x1 y1 is the solution. That means this is the solution. Therefore, x1 plus k b by g, y1 minus k b by g is the solution of 1. x1 plus k times b by g, y1 minus k times b by g is the solution of 1. So, what we have shown is, if x1, first of all there is the solution x1 y1 provided g divides c. Now, any other solution xy you can write in terms of x1 y1, and x will be x1 plus k times b by g and y will be y1 minus k times b by g for some integer k, and for any integer k this is a solution. So, you have got all solutions in terms of one solution x1 y1. So, we get this theorem, let ABC belong to Z, at least one of AB non-zero. Let G equal to AB. If G divides C, AX plus BY plus is equal to C has a solution in integers, and if G does not divide C, the equation has no integer solution. If G divides C and x1 y1 is a solution, then all solutions are given by x equal to x1 plus k into b by g, y equal to y1 minus k into a by g, where k varies over z, k in z. So we take a simple example. So solve two x plus 3y equal to 10. So here you are interested in finding interior solutions. The GCD of 2 and 3 is 1, and this divides the right hand side 10. Therefore, this equation we can call it as equation 1 has solutions in integers and in fact infinitely many solutions. And how do you get these solutions? In terms of a parameter. The solutions, so you should find out first of all one solution. So this one solution you can get by trial, or you express G as a GCD as a combination of the given numbers, and from that you can get. So here you can get a solution by trial, x equal to 2 and y equal to 2, that's a solution. So by trial x1 y1 equal to 2 2 is a solution. And so you get all solutions. So all solutions are, these are solutions in integers. X equal to x1 plus k times b. Now here ax plus by equal to c. This is 2x plus 3y equal to 10. So a is 2 and b is 3. This b is 3 and y equal to y1 minus k times a. Note that g is equal to 1. So actually it is, because g is 1, so a by g, that is a only, and b by g, that is b only. So that's why we are writing k times b by g, so that is just b. Here also minus k times a by g, that is just a. So x1 is solution, that is 2, y1, x1 y1, that's the solution. So you get a is 2, 2x plus 3y equal to 10. So you get x equal to 2 plus 3 times k, y equal to 2 minus 2 times k in Z gives all integer solutions. So you see that the values of x and values of y, they you can, if you take the next value of k, you have a change in the value of x by the value of b, that is 3 here. In general, x is increased or decreased by b by g, and similarly y is increased or decreased by a by g. You have to see what is the corresponding sign. This ax plus by equal to c, you can consider this as a straight line, and the solutions are integer solutions, means these are the points xy on this such a line, ax plus by equal to c. These solutions are points on this line with integer coordinates. So geometrically you observe that there are infinitely many values, integer values of x and y, which are both positive in this case. If you have a line like this, this is a line with positive slope. You can have a line like this also. Here also infinitely many coordinates xy are positive integers. Here infinitely many are negative integers on this side if you go. Here we have x is negative but y is positive. So this is what is happening for a line with positive slope. But if you take a line with negative slope, like you can consider a line like this. Here both x and y are negative. Here x is negative, y is positive. Here x is positive, y is negative. There is no solution xy in integers where both x and y are positive for this particular line. However, if you have a line like this, ax plus by equal to c, here this x plus by, let me look at this, equal to c. So if you put y equal to 0, so depending upon the value of c, so suppose c is positive, then I can put y equal to 0 and get x equal to c upon a. And here we put x equal to 0 and y equal to c upon b. Okay, so if the figure is like this, there is some possibility of solutions in positive integers, whereas for this situation there is no solution in positive integers. Here infinitely many positive integer solutions are there. So we discussed this, how many solutions are there with both x and y as positive integers. So one if ax plus by equal to c has positive slope, then infinitely many positive integer solutions. That is, both x and y are positive. Such solutions are infinitely many. If x plus by equal to c has negative slope, then there may not be positive integer solutions. As is clear from the figures. So suppose that A and B are positive and C is also positive. So suppose are positive integers and so it's C. Now for a solution x1 y1, all solutions are x equal to x1 plus k b by g, y equal to y1 minus k a by g. These are all solutions. So we want x1, say x and y, suppose both are required to be positive. So x1 bigger than 0 if and only if, so or rather say x bigger than 0 if and only, let us write in terms of x1, x1 plus k times b by g is bigger than 0, that is k b by g is bigger than minus x1, that is k is bigger than minus x1 g by b. Here b is assumed to be positive, so we can divide by b and the inequality remains as it is. Also, y is bigger than 0 if and only if y1 minus k a by g is bigger than 0, that is y1 is bigger than k times a by g, that is k is less than y1 g by a. So we get conditions on k Thus both xy bigger than 0 if and only if k is bigger than this quantity minus x1 g by b. So we can say k belongs to open interval minus x1 g by b and k is less than y1 g by a. K is in this open interval. K has to be an integer. So now look at the length of the interval. This open interval is, what is the length? y1 g by a plus x1 g by b, that is g into ax1 plus by1 divided by ab. But then ax1 plus by1 is equal to c, that's equal to gc upon ab. The length of this interval is gc upon ab. So how many integers are there in this interval? So one thing is clear, suppose n is, so this is some number which can be an integer or it can be a non-integer, it can be like 2.4, some such thing. So how many integers are there in between these two values? So if n is the number of integers in this interval, then the length of the interval, and like you can take 2.4, then 3, 4 and let us say 4.1. Maybe some interval of this type is there. There are two integers in between and the length of this interval is actually less than 2. But this number of integers is very close to the length of the interval, and we observe that number of integers in this open interval is satisfies this property that n minus gc upon ab is less than or equal to 1. So you get approximately the number of values of k for which both x and y are positive integers. So this gives an estimate, and similarly if you want non-negative solutions, integer solutions, then also this will be closed interval. So x and y are both non-negative if and only if k belongs to this closed interval minus G by A. And then also we have similar result. And then the number of non-negative integer solutions, this number satisfies, it is the number of integers between this and this. So it is, suppose this number is n1, mod of n1 minus gc upon ab is less than 1. So it is very close to less than or equal to 1. It is very close to gc upon ab. If you want exact number of positive solutions, then you have to actually see how many k are there which are positive integers and which are between the given numbers minus x1 g by b and y1 g by a. How many values of k are there? We have to actually count. So if you know one solution x1 y1, see this is independent of the solution x1 y1, g, c, a and b. If you want to know exactly, then you should use the solution x1 y1, and from that you can find out exactly how many positive solutions are there. So from where we will start? What is the first number positive integer which is bigger than this quantity? It cannot be equal to this. Even if b divides x1g, you cannot take this value if you want positive solution x and y. Solution x and solution x and y both are positive. So how do you get this number which is to the right? See, suppose you have, this has to be an integer. Suppose this is 3 here. I cannot take 3, I should take k equal to 4, next one. Okay, because it's open interval. So how do you get that integer to the right of it? So it is actually, what is the integral part? For example, take this example, suppose it's 2.4. What is the integral part of 2.4? That is 2. You add 1 to it, you get 3. Okay. Whereas if you take, suppose this itself is already 3 and I don't want 3 but I want 4, next one. Okay. So integral part of 3 is 3, and then add 1 to it, that is 4, and here also so that we get it. So let me consider for any a in R, the nearest integer to a which is greater than a is given by integral part of a plus 1. This is the answer provided. Whether a is an integer, then also this is the answer. If a is not an integer, then also you get this answer. Now I want, given an open interval like this is, I want an integer which is smaller than this. And how do you get that? So for any b in R, the nearest integer to b which is less than b. That is, even if b is an integer, we don't take it, we take smaller one, is so it is minus b you take minus of this and minus 1 minus integral part of minus b minus 1. So take an example that if b is an integer, then this quantity will be just b minus 1, that is what we want. Whereas if b is like 2.4, minus b is minus 2.4, its integral part is minus 3, and just take minus of this which is 3 and subtract 1. So that becomes just 2, and so that is the number to the left of. So minus integral part of b minus 1 is equal to 3 minus 1 equal to 2. This is the integer to the left of the number b equal to 2.4. Okay, so the values of k that we should take, therefore we take integers k such that this number is there, minus x1g by b integral part of this plus 1 less than equal to k less than equal to minus of integral part of minus y1 g by a minus 1. Okay, minus integral part of minus of this minus 1. These are the values of k. How many integers are there which satisfy this property? How many integers are there? See, this is now an integer, this is also an integer, and k can start from this end here. So usually, you know, how many integers are there from say 3 less than equal to k less than equal to 10? How many integers are there? The method is you subtract these two and add 1 to it. There are 8 integers, 10 minus 3 plus 1. So if you want k such that k is between this integer and this integer inclusive, both are included, then you take difference of these two and add 1 to it. Number of such k is minus integral part of minus y1g by a minus 1 minus integral part of minus x1g by b. So minus 1, this plus 1 here. So I have written this number as it is here, minus this number I have written over here, and add 1 to it. Add 1 to it. So this minus 1 and this plus 1 gets cancelled, and the answer is minus x1g by b integral part minus y1g by a integral part minus 1. This is the number of, this is the exact number of positive solutions. Thus, for a, b, c bigger than 0, number of integer solutions of ax plus by equal to c with both xy positive is given by this formula, minus x1g by b minus y1g by a minus 1. Okay. So we have approximate formula which differs from GC upon AB by at most 1, and this is the exact formula in terms of a known solution x1 by 1. This is the number of positive solutions of the equation. You can also find number of non-negative solutions in a similar fashion. So this is the linear Diophantine equation that we have studied. We can also think of an equation like x square plus y square equal to z square. This is an equation of degree 2 in 3 variables x, y and z, and any positive solution like 3, 4, 5, this is a Pythagorean triangle, right angle triangle, sides are 3, 4 and 5. 3, 4, 5 is the solution of this 3 square plus 4 square equal to 5 square, or 5 square plus 13 square, 12 square equal to 13 square. So we can have plenty of solutions of this Diophantine equation also, and the solutions can all be described by means of a formula. First note that for this equation, if x and y we have a common factor, then that will also divide z, and we can divide by this common factor of x and y, which is also common factor of x, y and z all, and then we get what is called as a primitive solution. So xy or x0, y0, z0 is called a primitive solution of this equation 1 if the GCD x0, y0, that is the same as GCD of y0, z0, which is also the same as GCD of x0 and z0, which is also the same as the GCD of x0, y0, z0, and that's equal to 1. The GCD of x0 and y0 is also equal to GCD of x0, y0, z0, because that has to divide z, and so this is what you should note. So if there is a common divisor, you divide by that and then you get what is called as a primitive solution. Now, from a primitive solution, if you know a primitive solution like 3, 4, 5, that's a primitive solution. You can multiply this by 2, say 2 into 3, 2 into 4, 2 into 5. So 6 square plus 8 square equal to 10 square. So from a primitive solution you can get other solutions. So it is sufficient to find out primitive solutions. Now how do you get primitive solutions? So there is a formula for primitive solutions. Also one notes that if x0, y0, z0 is a primitive solution, then x0, y0 are of opposite parity, that is one of them is even and the other is odd. One of them is even and the other is odd. Because if suppose x and y are both even, then 2 is the GC, 2 divides both x and y, so 2 will divide z naught also because of the equation x square plus y square equal to z square. From that you will see that 2 divides. So both cannot be even. If both are odd, what happens? Just check that both are odd. This is not possible. If x naught square plus y naught square equal to z naught square and both x naught, y naught are odd, then left hand side congruent to, see, square of an odd integer is 1 mod 4. So x naught square is 1 mod 4, y naught square is also 1 mod 4. 1 plus 1 mod 4. Therefore, right hand side equal to z naught square is congruent to 2 mod 4. And this is a contradiction. Okay? Because z naught square is congruent to 2 mod 4 means z naught is even. But if z naught is even, z naught square is 0 mod 4, not 2 mod 4. Okay? So that means at least one of x naught and y naught is odd and another is even. Both are odd, both are even, that's not possible. Now if you have x naught and y naught, one of them is even, the other is odd for a primitive solution, and we can assume that y naught is even. By interchanging x naught and y naught, we can assume that y naught is even. And then we can give a kind of formula for x naught, y naught, z naught. So that's a theorem. Also we can assume that they are positive, because from a negative solution we can immediately get positive solution by changing sign. So primitive positive solutions of x square plus y square equal to z square. This is a Diophantine equation, and we want Rs are integers such that R bigger than S bigger than 0, Rs equal to 1, and R and S are of opposite parity, and Rs are of opposite parity. So, and from primitive solutions you can get all solutions by just multiplying x, y, z by some common integer. Clearly, if you take x square plus y square, that becomes equal to z square. R square minus s square square plus 2r square is equal to r square plus s square square. So this is a solution. All these are solutions. Solutions of this with y even. One of them is even, the other is odd. So y we are taking to be 2 times rs, that is even, and r square, and so x is actually odd. X square plus y square equal to z square minus x square equal to y square, z minus x, z plus x equal to y square. Now divide, so this is now odd and odd, so difference is even, this is even, z minus x by 2, z plus x by 2 equal to y by 2 bracket square. And now you can check that these two are co-prime and this is a square. So product of two integers which are co-prime is a square, then each of them should be a square. That's what can be proved. And so this we can write as r square and this is a square. Okay. So these are co-prime integers can be checked and their product is a square. So this is square, call it as r square, call it as a square. If you add these, you get z, which is r square plus s square. This minus this will be equal to x and then that is r square minus s square, and y you can write as 2 times rs. That is the way. So you are using that if product of two co-prime integers is a square, then each of them is a square, and that gives you the formulae given there in the statement of the theorem. Okay.